Okay, everyone. Hello. Today we are going to be talking about populations. Welcome back to class, and I hope everything's going well for you. So, specifically, we're going to think about what population ecology is. I'm going to lay out a little more of a definition of ecology and how populations relate to that. We're going to talk a lot about what factors influence the size of populations and how they change over time. You're going to do an activity that helps you better understand how population sizes and changes are measured over time. And then along the way, we'll do a lot of thinking about why it is important to study populations. But before we get into all of that, I've been having a hard time just sitting here. And so I thought we'd take a little field trip to start with today. So come with me, and we're going to take a little trip to Mendon Ponds. All right, let's head back inside. All right, so that was a little trip out to Mendon Ponds Park. If you haven't ever been out to Mendon Ponds, it is not far from the RIT campus. Let's see, let me zoom out a little bit. There's RIT. Oh, it's about 15-minute drive from RIT. And one of the things that's really fascinating about Mendon Ponds is that it has all of these different glacial features. 10,000 years ago, when the glaciers melted, deposited a lot of sediment. And if you took New York State Earth Science, you've probably learned some of these terms, but there are these really neat kettle ponds that were created when giant blocks of ice melted and left these depressions. And they make really interesting places for studying spring and vernal ecology, right? So a vernal pool is any pool that is temporarily wet, any sort of pond that is wet mainly in the spring. And they're really neat places to study ecology because they usually don't have fish. So it's a place where salamanders and frogs and other sorts of organisms that would normally be eaten up by the fish thrive. And so what you heard in that video was just a little sample of what the calling frogs sound like in the spring. If you ever never had a chance to experience it, try to find a way. If you're home right now somewhere where the frogs are calling, take the time to go find them. You can still go outside, just don't hang out with any other people. So, but I also wanted to bring that into the situation because as we think about populations today, it's a good way for us to think about if we wanted to know how many frogs were in that pond. How would we figure that out? If we wanted to know if there were more frogs this year than last year, if there's an increasing trend in the number of frogs, how would we study that? And what does that mean for the bigger picture, right? If they're increasing or decreasing, why? What sort of factors are coming into play? Is there a maximum size of the population that a pond like that can support? Those are the things that population ecology hopes to better understand. So we're going to switch over to the lecture now. I've got some slides, and this will give you a good introduction to the topic of population ecology. All right, so I want to start with a basic definition of ecology. So ecology is, and I always add this, in the scientific study of the relationship between living organisms that include humans and their physical environment, right? So ecologists work really hard to understand the connection between plants, animals, bacteria, fungus, and the world around them, right? And then in the broader picture, ecology gives us some information about ecosystems and how we can sustainably live within those ecosystems. And this definition comes from the Ecological Society of America. One of the things I always want to stop and point out is that ecology is a scientific way of knowing. So people have understood their relationship to the living world around them and the relationship that the organisms they share the world with have for as long as there have been people. And sometimes we need to stop and remember that and understand that, what people know, what's often called traditional ecological knowledge, has been gained over thousands of years, and it may not have been done through rigorous scientific study, but it's just as important way of knowing as sciences. But today we're going to really focus on the scientific way of knowing ecology and the relationship things have with their environment. So I just want to lay out these main ideas. I'm really going to focus on this idea of everything being an ecosystem and systems thinking as the important ideas in ecology today, right? We also have to really remember that evolution and ecology are related. That's an exciting field of research. Scale matters, so you can think about ecology from everything that is living on your thumb as an ecosystem to the whole earth as its own ecosystem. And then there are a few ideas here that we really need to think about as we look at the impact people are having on the earth. One, there's always limits to growth. Two, there's always a cost. And three, people matter in this situation. So we'll go into some examples of that today, but those are the ideas that I just wanted to lay out, basically related to ecology, right? And within ecology, we have these different fields of study and levels of organization. So we have the individual species level, we start there, so that's kind of where we started our study of ecology, thinking about behavior, how an individual behaves. And then a collection of individuals is a population, collection of populations is a community, collection of communities is an ecosystem, right? And within each of these different levels of organization, there are completely different fields of study. I personally am most fascinated by community ecology and ecosystem ecology because those represent the most complex relationships and sometimes the hardest things to tease out all the different variables and understand the patterns that are occurring. But there are always patterns that can be found. And so they make for really interesting fields of study. All right. I also want to take a minute right now to switch us into kind of, as we think about ecology, we need to think systemically, right? So looking at things from different directions, thinking long-term and short-term and how those two things are related. Also thinking about the cause and effect, right? And how rates of change impact what we see today, tomorrow, and lots of steps into the future, right? And it's I've brought this idea up before we went away for break, but this is similar to the ideas in ecology. The ideas of systems are that everything's connected and the different pieces function together to act as a whole, right? And we get a system, for example, a population is much different in its impact, and we need to understand a population as a whole rather than just a bunch of individuals, right? And systems have predetermined behaviors, but it is not necessary. But things can change the way that the path that they take, and there are just three basic ideas, right? The flows, reservoirs, flows, reinforcing and balancing feedback loops. So take a minute when you look at this slideshow to look at the World Population Clock website. Links here. But if we take a look, this is what the human population trend has been as long as people have been studying this, right? So some things to stop and do is, what do you notice? What do you think? And, how do you feel about what you see? And it represents kind of a basic pattern that we're going to talk about in a minute. But at first I want to just lay out this basic definition of a population, right? Population is a number of individuals of a particular species in a certain area. And that area is defined however whoever's studying it wants to define it. So, in this example that I gave, these are two different frogs. There's up at the top is a peeper, spring peeper, and on the bottom is a wood frog, and those are two of the frogs we might have heard at that pool that we stopped at Mendon Ponds. But we can choose one of those ponds as the area of the population, or we can choose all of Mendon Ponds Park as a population. And some of it depends on whether or not we think that the individuals can move in between the different pools. And that's outlined in your textbook as they talk about metapopulations, and from a conservation point of view, that's a really important thing to think about. So after talking about the definition of a population, we need to think a little bit about how populations grow or decline, right? So the birth rate, number of individuals that are born, the death rate, number of individuals that die, will give us a basic idea of what a population growth rate is, right? And there's this idea of the maximum intrinsic growth rate, which is the fastest rate any population can grow given ideal conditions. So this equation adds in two different ideas, right? So the I and the E represent the total number of immigrants into the population, and the E represents the total number of immigrants. So how many individuals are leaving and how many individuals are coming into the population, right? Can give us a change in population over time, right? So we start at NT, add in births, deaths, immigrants, and emigrants, and we get that number. I found this article here, Changes in Frog and Toad Populations Over 30 Years in New York State. I posted that up on my courses. It's an optional read, but it's just a way to see how these equations and these ideas are used to better understand our ecosystems. Represented in a systems format, this is how populations change, right? On one side we've got the births and the birth rate. On the other side we've got the deaths and the death rates, right? So the population is a reservoir of the number of individuals leaving versus coming in. This was more accurate. It would include immigrants and immigrants, right? And so all populations can grow exponentially through this reinforcing feedback loop, right? So for every birth, it adds to the population, and as the population grows, there's a larger potential for births, which then means there's a larger population, right? And we get this exponential growth curve. That's just another way to represent it, right? So as the population grows, it affects the birth rate, right? If there were 2 individuals to begin with, and they each had 1 baby, then that would be 4, right? Now that there are 4, that same rate of growth would give us 8, 16, and so on, right? And this diagram shows us how populations can grow exponentially, and it's just another kind of more complex way to think about things, because this has the per capita growth rate not changing even if the population gets large. R is the population growth rate, right? And N is the number of individuals. And over here we've got logistic growth that's based on a carrying capacity. So as we move forward, we want to think about this kind of thing of what are the sorts of variables that are going to impact the growth of a population. You know, we're back here at Mendon Ponds. Here's another one of the ponds that's now, was frozen 2 weeks ago when I took this picture, but now full of calling frogs. And if we thought about how many frogs are there this year versus last year, what would be affecting the birth, the death, immigration, emigration, and then what sort of environmental conditions might be affecting the growth rate. Is the warmer winter going to be better for them? Is a colder winter going to mean a decline in populations? Is a change in pH of the water going to cause an increase or decrease in population? And so we can kind of break those down to this idea that we introduced in behavior is proximate versus ultimate, right? So the births are the proximate cause, but then what is the ultimate cause of an increase in births, right? Deaths are proximate cause of population change, but then what's really causing those births? Immigration and emigration as well. And this is what's can be really cool about studying ecology and things like population ecology, is there may be other forces that are 2 or 3 steps away that we don't immediately see, but if we think deeply and we look deeply, we might see that frogs are moving from one area to another because there was a change in predators that they're trying to escape predation, or maybe there was some sort of change in hydrology, that the water flow changed because there was some sort of development that happened somewhere. So those are all the things that, if you want to think about how populations change over time and grow and shrink, these are some of the things you need to think about, right? So as we move on to talk a little bit more about carrying capacity, we also have these two ideas that we need to think about, that there are density independent limiting factors to the size of a population. So there are no feedback loops involved in this. These happen regardless of the size of the population. Natural disasters like volcanoes and earthquakes, storms, are things that will limit the size of a population. But then there are things like density dependent factors that do represent feedback loops, that as the population size grows, these things come into play, that are going to slow the rate of population growth. So food availability, mate availability. These are density dependent factors that limit the size of a population, right? So the environment also limits the size of a population, and the carrying capacity is just a way to understand how large of a population a particular environment can support indefinitely, right? So this is where the idea of sustainability comes in, is, that we need to maintain the population rather than seeing some sort of overshoot and collapse kind of situation. And so we get this S-curve, or a logistic growth curve, when a population starts to come under the factors of density-dependent population growth and approaches a carrying capacity, right? And so we, again, have this exponential growth up to a certain point, so we've got the reinforcing feedback loop. And then somewhere along the way, the negative feedback or balancing feedback loops come into play that slow down the size of the population growth, and limit the size of the population, right? And so this diagram just shows that built in, that the amount of food available is going to create a balancing feedback loop, that less food means more deaths. Excuse me, right? And this is just another way to look at balancing feedback loops, right? And that behavior that we see, the oscillation in the graphs often when we've got balancing feedback loops. All right, and so this is just another diagram that shows how these feedback loops work. And as you get more complex diagrams going, you start to see that food are actually other populations of organisms, and so all of these populations interact with each other, right? And so this is just a way to show how population and the availability of food are related to each other and influence each other. And this one is just another systems diagram that just shows this complexity, but related more to people, right? So population and soil and food availability are all related to each other. That's why it's so cool that soil is one of the classes you take as an environmental science major, because it is at the root of everything. And then I just wanted to bring this into the conversation today, that in 1972, some of this modeling, these population models were fed in to a computer for the first time. They built these computer models and tried to figure out what the limit to growth was for the human population. So you'll see the curve here for human population, and this is what they predicted the trends in population would be, and food availability and resources in this limits to growth. You can find this book. Turns out that their predictions weren't entirely accurate, and it's a good thing to think about, that behavior of systems is predictable but not predetermined. And it's something that we are looking at right now as we are trying to figure out how to stem the growth of the coronavirus, the COVID-19, that there are some predictable patterns in the spread of the disease, that it's going to spread exponentially. But then this whole idea of flattening the curve, what is the rate of change and growth going to be? All right, so for the activity today, or your to-do list, as we go off, that's my lecture on population growth. There's also actually a really good Khan Academy one out there. If that one left you a little confused, I would highly recommend taking the time, right? But here's a to-do list, right? So you've already watched the video. Take a minute to study the slideshow a little deeper. Read chapter 44. That's a really complete discussion of population ecology that you'll learn a lot from. And then there's an activity for you to complete, measuring population size. And so I just want to switch to that real quick. That it's got 3 different methods for estimating the size of a population. So it just gives you a little idea of how this works. Visual estimates, but can also be audio estimates. They're using some interesting technology to study, again, like the population of frogs by listening, trying to figure out how many different frogs you can actually hear. But visual estimates, quadrat sampling, and this helps you think about the difference between a skunk cabbage population and a jewelweed population. Skunk cabbages, if they were distributed evenly, versus clump populations, and comparing the estimates you get there, and then finally mark recapture methods that are often used. Got this little picture of this frog here. It's got a little tag, but there's mark recapture is a really common way to study the populations of organisms that move around, and it's really simple and elegant. So that activity is ungraded, but will definitely be assessed on the exam. People have been starting to ask questions about the next exam that will be on April 16th. Pay attention to some updates on that coming soon. And then I also threw out some other optional videos to watch here. There's this one here about exponential functions. It's a classic lecture if you're really into like what were they saying back in the day. But the other one's a TED Talk, help you better understand exponential growth. And then I got our Feel Good Photo Gallery that some of your classmates submitted pictures here. And so, if you have any questions, let me know. We'll have office hours from 8 to 9:15, and then again from 12:30 to 1:45 on Tuesday and Thursday. If you have any questions, please come by. Just use the Zoom tab on my courses. All right, good luck getting this done, and have a good day.